recording. So I'm going to talk about recommender system today. So here's the first is the wiki definition for recommender system. And you can call it a recommender system or recommendation system or recommender engine or platform. And the basic idea is to filter the information and recommend something you may prefer. And nowadays we almost kind of live in the world of recommender systems. If you go to any e-commerce website, Amazon, Wayfair, Walmart, anywhere, and they're going to recommend products to you. And we use Netflix to see videos, or maybe YouTube, and Google News to see recommended news, and Pinterest for images, Spotify for music, Facebook for friends, LinkedIn for your professional friends, and Occupied. It's actually online dating website.
OkCupid.
Yeah, OkCupid. Okay, so it's an online dating website, and they also have some underlying recommender system running on that platform. So basically, a recommender system, and it's just some kind of a platform. It can automatically recommend items or products to users, and which are likely to be of interest to the users by utilizing historical information. So I think a key thing and key points are automatic and also historical information. And of course, we wanted to know how to build a recommender system. Here are the sort of so-called non-personalized recommender system. We've been using those systems for a long time. They're basically based on either expert knowledge, top 5 winter boots for girls, or today if you go on the website will be top Cyber Monday deals, and based on either expert knowledge or just simple aggregated statistics like best-selling books, etc. Of course, the drawback of those recommender system would be it's not personalized. So we want to know how to build personalized recommender systems. We're going to go through some of the basic methods like content-based and collaborative filtering and latent factor model. I color them one is sort of in salmon pink color and based on another sort of a green and based on what kind of information they use. If you use information just about the items, the products, and those are content-based. But if you want to use user item interaction information, and those are the collaborative filtering, also latent factor models. You're going to find out one recommender system is not enough. You have to use hybrid, meaning you're going to combine them. Also, a lot of these methods listed there sort of get popular because of this Netflix competition. And that's before Netflix starts streaming. That's like around the time Netflix owned, mail, DVDs, and collect information based on users' rating on certain movie. But now they can get a lot more information about us. When you start watching this, when you stop, and have you ever resumed, and have you click any of the recommended videos? So they get a lot more information about us, and this is why actually I add a link to the paper. If you click this Amazon recommender system, I think it's not the Amazon, but Netflix. So they nowadays for Netflix, and they combine a lot of recommender systems, not just a single one. Like they have a rows of recommendation. So in short, nowadays the recommender system. People use, combine them, and they also use more sophisticated methods. So I will give you a brief introduction about some of the sort of state of the art recommender systems. They're all based on deep learning and deep neural network, and I just highlight some of the kind of main areas. Okay, so we're going to talk about how to build a recommender systems. First one is a content-based method. Very easy. We basically, we as a company build the catalog of the products. So we know how to represent every item. You can think of the item as movies or articles. So we can represent each item by a d-dimensional feature vector. So you can think about, for a movie, we can, use features like, when the movie was released, what kind of a category or the genre of the movie, who is the director, and who is the main actor or actress. So a lot of information you can use to describe an item. So this is how we build an item profile. Basically, we're going to think about every item and as a point in a d-dimensional space. So those are the blue dots. So those are the items. And then we can also build a user profile in the same space. How we build a user profile? Sometimes some website will directly ask you, what's your interest? Are you interested in this movie or the other type of movie? Or you can just, based on what kind of movies he or she watched recently, and look at those movies feature vector and do some kind of a weighted average of them. The weights could depend on the latency. If a movie just watched recently, get higher weights. Movie watched later, get lower weights. So then you can use the items a user selected or watched and as a proxy to get the user profile. So you can embed users also in the same space. Those are the yellow squares. Right. Then now items or users are all in the same space now. Then we can measure the preference as a distance. And for example, for this user, suppose all those 3 items or movies this user hasn't watched before, then which one we're going to recommend to this user? We're going to recommend this one because this is the closest to the user profile. So it's very simple. So the key idea is just to figure out a way to describe item in a d-dimensional space. And then we can find out a similar way to describe a user in the d-dimensional space. They're called item profile and user profile. Now, if they are in the same space, then Euclidean closeness represent preference. And then we can start recommending. Okay? Clear? So the advantage would be when we are building this, when we want to recommend to this user, we don't need to know other users' information. We only need to know your profile and the item's profile. So imagine I'm building such a website. I have this feature. I can start recommending on day 1 because we don't need to wait for any user-item interaction and data. And we can recommend new and unpopular items. So even this item is not very popular. Not many people watched it or purchased before. But once we find somebody are looking for this kind of feature, we're going to recommend this item to the user. So what's matter is the feature, not the popularity. And similar, if a user with a very unique taste, and meaning not many users are like this particular user, it doesn't matter as long as we know what feature you're looking for, we can recommend closest items to you. And also, it's very easy to interpret or understand why we recommend this item to this particular user. Because certain features he or she is looking for. But the drawback would be those recommendations very routine, and we never recommend anything outside this user's profile. And in some sense, what we recommend would be really substitutes, not complements. We won't find anything new for this user. And the most important drawback is it is very, very difficult to find a proper set of features to describe items. Like movie, articles, images, and dress for girls. They're very difficult to find the features to describe it. So that's a drawback. So this is why people switch to the so-called collaborative filtering method. What's central to this CF method, collaborative filtering, we need this matrix, the interaction matrix between user and item. So you can think about this matrix R and n by n. So each row represents a user, and each column represents an item. And then we have some entries we know, and we can get the information explicitly. For example, in Netflix, and they will ask you to rate this particular movie, scale from 1 to 5. So you know explicitly know whether this user like these items or not. And sometimes you can get implicit information, like you show this movie or this item, and does this user click this before, or so you sort of get some implicit information about the interaction between user and item. And I do want to point out it is very difficult to construct this R matrix. In Netflix, yes, there are other ratings, but in a lot of scenarios, it's very difficult to construct an R. So one of the difficulties is very difficult to differentiate. You don't like it, or you're just not aware of this item, right? And so the missing means negative, or or something different. And I would just leave this as a sort of one of the challenges for a recommender system. Let's right now assume we already have this R matrix, and of course we won't have every entry. So a lot of entries going to be missing, which are the question marks. So the goal of recommender system is just to fill in those missing values. So this is why a lot of times, if you do a Google search on recommender system and you see some other keywords like matrix completion, and it's a related keyword because we are trying to complete this matrix and some entries are missing. Now, why this matrix R can help us to define features? Now we can actually start for every column correspond to an item. Then we can use those red column, although some are missing, but we can use those red columns as a new feature for items. So we can define similar items based on how other people like this item. And similar, we can find similar users. Every row, which is the green line, represent the user, which are the users are the feature for every user basically, and is this user's response or preference over those items. So every row now will be the feature vector for users. And so there are two types of, so the idea of this collaborative filtering are basically based on the following two approaches. One is based on the green rows, they call it user-based and collaborative filtering. And the idea the rationale is that items tend to be liked by similar users. Meaning if two users are similar, and user A purchased this item, and then user B, which is similar to A, may tend to purchase item 2. So you have to define similar users. I'll go through the details on the next slide. Similar, you can do another type of a collaborative filtering by looking at similar items. And so users tend to like similar items, meaning I purchased item A, and now based on looking at the profile of the items, which are the red bars, I know item A is similar to item B, and then it's very likely I may want to purchase item B too. So that's sort of another framework. So it's basically for the same matrix, you can either filtering through rows or through columns. Of course, in addition to this matrix R, a very central notion is similarity measure. We have to figure out a way to define how users or items are similar to each other, right? And there are vectors, and with some missing values. And so there are commonly used similarity measures. One is that Jaccard similarity is often useful for binaries. So for example, for this A and B, suppose we ignore the rating. This is an example from this. I attached some of the, let's see. So I attached some of the notes. One is from Stanford's Mining Massive Datasets notes. I think this is an example from that book. So HP is Harry Potter 1, 2, 3, and Twilight, and this is Star Wars 1, 2, 3. Okay, so that's the movies. And ABC will be users. And we can ignore the rating, and we can just see whether they watch this or not. Then it could be binary. So for example, for A, the binary vector, and 1, 1. And for user B, user B watched those movies. Okay, so if I want to measure Jaccard similarity between A and B, the numerator will be 1 because they share only one movie, and the denominator will be 3 times 3 because each watched 3 movies. Okay, so that's for the Jaccard similarity. Another similarity would be the cosine similarity, basically inner product normalized by their L2 norm. And whenever something is missing, just discard that entry, which is the same as treated as 0. And so you can calculate the similarity between A and B and every pair. But you quickly realize the drawback of the cosine similarity because you basically interpret missing as negative because it's 0. That's the lowest score. So instead, people do centered cosine similarity, and sometimes people call it Pearson correlation. Basically, the ordinary correlation we use. So what is the centered cosine similarity? Again, you take the A vector, you calculate the mean. The mean is only calculated based on the observed data. So it will be the 3 numbers summed together divided by 3. And you subtract that mean from each entry. Right? And then you do the same for every row, and you then calculate the inner product between A and B. Okay?
I have a question on Jaccard similarity. And if A and B are exactly the same, will the similarity be 1?
So the Jaccard similarity, if A and B are exactly the same, actually it's not 1. Yeah. So maybe this should be the union. Yeah, I think that should be the union. You're right. I actually paused here, so that should be the union. Okay. Then in that case, if it's a union, that will be numerator is 1, and what is the denominator for A and B?
5.
Yeah, 5. Right. Good. Yeah. So then in that case, you're right. Then if A, B are the same, then makes sense to be get the highest similarity. Yeah. Okay. So let's back to the center cosine similarity. So the ordinary cosine similarity, at least for the movie data, and there's a disadvantage because missing is actually treated as negative. But once we do centering, then missing, which is regarded as 0 now, but 0 is actually the average. Makes sense. And also can handle tough or easy readers because you want to remove the individual effect. For example, B could be a because previously for the Harry Potter 1, B the B's rating is 5, but it's kind of a but you can see B's tend to give all the movies he or she willing to rate a very high score. So you want to remove that effect and then look at the similarity. Okay. Okay, so let's take once we have this R matrix, once we decide how to pick what kind of similarity measure to use, then let's look at how we're going to operate this user-based collaborative filtering. So, for example, for this case, so user-based meaning we're going to first find similar users. So if you want to run this algorithm, there are often a k-nearest neighbor, the k value you have to specify. So k here is equal to 3. So for example, the user, it is the user at the bottom in sort of highlight in orange. And first we're going to use one of the similarity to find the 3 nearest neighbor for this user, which are highlighted in blue. Okay? And then we're going to use that 3 users rating to fill in those question marks for this user in orange. Here, let's just do simple average. We could do weighted average, but let's just try simple average. For example, let's look at how 3.5 is computed, which is because for the 3 similar users, for this user, the first item is missing, so we won't be able to use it, but we can pick those 2. So 3 plus 4 divided by 2. So that'll be our estimate for this first question mark, the preference for this user in orange for item 1. And similarly, let's move to, for the second item, because the second item is question mark, so we have to fill in this question mark. Among the 3 users, only one of them actually, we only get rating from one of the user, so it's 4.0. Okay, let's just grab from this value. And similar, let's look at how we calculate this question mark. And those are 3 similar users. Their entries are those 3 numbers. We get these 3 numbers and calculate the average, and that will be our prediction if we use the user-based collaborative filtering neighborhood size 3. That's our prediction for the 5th item. Okay, makes sense? And you can easily extend to the weighted average, meaning when you are calculating the average, you want to assign weights to the user which is closer to this user of interest. Okay, makes sense? And then you realize there is a drawback, because what if, for example, hypothetically at a certain point, suppose the first 3 users are nearest neighbor for some user. And if we want to know the rating for item 7, everything's missing, right? So it's not and you won't be able to get any information. So this is why in practice, you can easily fix that problem, meaning when you pick the 3 nearest neighbor for item 1, you're going to pick the 3 nearest neighbors that also rated item 1. So the nearest neighbor would change depending on items. Make sense? That's just some additional things you need to handle in your code. Now let's look at item similarity, item-based collaborative filtering. So meaning if we have this data, we're going to look at those columns and build similarity among those items. So we get our similarity matrix now, just item versus item now. Okay. Then here's a particular user. We have the user purchased or at least showed interest for item 1, 5, and 8. Now we want to fill in those missing values for the other items based on the rating for 1, 5, 8. How we did that? Let's look at, for example, how we calculate the rating for item 3. Okay, so for item 3, let's look at how item 3 is similar to item 1, 5, and 8, because we only get rating for 1, 5, 8. Now we want to know item 3, 1, 2, 3, yeah. Item 3, the similarity with item 1 is 0. And its similarity to item 5 is 0.4. And the similarity to item, sorry. Yeah, okay, I think we write it this way. We look at item 3 and we look at the similarity between item 3 and all the other 8 items. Let's find the 3 nearest item closest to item 3. So they are right? So item 2, item 5, and item 8, right? Because the higher value means they're more similar. But item 2 is still missing, so we won't be able to get any information. But we do know item 5 and item 8, which this 4 and 5. So you're going to calculate your, based on the item similarity, you're going to calculate your rating or preference for item 3 to be 0.4, which is the weight we assign for item 5, times 4, and 0.5 times 5. Or you normalize because the weight is 0.5 and 0.4, so you have to normalize it. So you divide it by 0.9. So that you get 4.6, and that will be our estimate for item 3. Okay. Let's do another calculation. How we compute the item-based collaborative filtering for item 4. So for item 4, the nearest neighbor would be item 1, item 2, and item 3. Oh, sorry, I cannot do item 1, 3.2. Maybe there is a tie, so they actually move 1 down. So there actually are 3 and there are 4 neighbors. But for item 4, so you're going to find out among the, so I think that in this case they have a tie, so they actually include all of those numbers. So maybe k is equal to 4, because they're all colored. No, I think it's 3. Yeah. So for the item, how do you get the 3.2? Well, it basically is 0.3 times 2, because our weights for the first item is 0.3, and the first item is, the rating is 2, and plus 0.2 for the item 8, because all the other are missing. So you normalize by 0.5. So that's the number, and that's the rating you assign for for item 4. Okay. Make sense? So in short, when you are doing itemized item-based collaborative filtering, you build a similarity between items. And then you look at a particular user, in this case is the user in orange, and then you basically wanted to fill in the blank values based on the items this user already rated before. In this case, 2, 4, 5. But how you assign those weights, which basically depends on the item similarity. We'll try to fill in the second blank, which is the preference for the second item. You want to use, you're going to do a weighted average of, the weights over the item 1, item 5, and item 8. And the weights are determined by the similarity measure. And sometimes people also use a nearest neighbor to only look at a particular subset of those items. Do some normalization. Okay. Here I did a weighted average, but you could do unweighted. Okay, questions? Okay, pros and cons. So there are 2 basic methods for personalized recommendation. One is content-based. We describe the pros and cons, and usually one's treasures is another person's one's trash is another person's treasure. So it's always like the pros will be the cons and cons will be the pros. Let's look at this look at the collaborative filtering. And the advantage is we don't need to define features anymore. So the user interaction becomes a feature. And apparently we can recommend outside the user's profile. Wait, this one is not right. We shouldn't have this. But the drawback would be you cannot really operate your algorithm on day one. You have to sort of wait for your algorithm to be live your platform to be on for a while, collect enough user item interaction data, and then start recommendation. Also, if there's a new item you just add to your catalog, there's no interaction data available, then you cannot recommend. Or if some item is really unpopular and nobody read that movie before, and you cannot recommend that movie to other people. Another is so-called popularity bias. If a movie which is watched by many people, liked by many people, there's a popular items, and you tend to recommend this to everybody. That's sort of against the purpose of personalized recommender system, because you want to recommend, kind of a personalized, items. Another issue is often known as the cold start. It's just when there's a new user or new items, how you're going to get user information to start recommending. So the both has pros and advantage and disadvantages. But for both approach, the challenge there in all those approaches, one of the key computation challenge is how to efficiently find nearest something in a large data set, right? Even in a content-based, if I send out a query and there is a there's a feature, but how can I find out the nearest item? In all the collaborative filtering approach, you also have to find the nearest like the k-nearest neighbor. So that's actually if your data set is huge, imagine Netflix or Amazon, and that computation cost is really high. So there are a lot of approximation algorithm involved, and sometimes people do clustering, like they cluster some of the items, cluster some of the users ahead of time, and then offline, and so they can do that more efficiently. Now for collaborative filtering, and I mentioned there are two approaches. One is sort of based on the user, another is based on items. And which one works better in practice? What will be your guess? Intuitively, which one would work better? I think that really depends on the underlying platform. For a lot of e-commerce website and for Netflix, they find out the item-based collaborative filtering works better. And the reason is we humans are such a hard to understand creatures. It's hard to so items are inherently similar. So similarity is a much more meaningful metric. So you can talk about two movies are similar, two items are similar. But it's hard to define two people are similar. Even when we watch movies, we could have different modes, right? Friday night, the movie you want to watch. Also, sometimes cold winter night will be different. So this is why they find out item-based perform better, and this is why I think content-based approach is actually there are definitely some merit for content-based approach, because content-based approach is also trying to figure out a way to find, use a feature to describe items. So you're going to see some of this content-based approach going to come back, because due to the same reason, it's easy to define features or similar on items and the product you wanted to sell. And, it's much more meaningful to find similar items and start recommending to people. So that's an interesting thing to learn. And so so how we're going to find the feature for items. As I mentioned before, one of the reason people move from content to collaborative filtering, because it's very difficult to find a feature to describe an item. And the item is like movies or images. So people move to this new type of a method called latent factor model. Again, we're going to focus on this rating matrix R. The key idea is just to decompose this matrix, singular value decomposition, decompose this matrix as a product of two matrices. They are much more narrow, with sort of k column, and k columns for the blue and k rows for the pink. So now you can. So if by R, every entry of R is already there, it just basically means you're going to do a singular value decomposition. So R going to be written as U times V transpose. And there's some kind of a ambiguity here because the normalization, let's just ignore that at this moment. And then we can get this decomposition U times V. And here, the columns of U is denoted by D. So now you can imagine, you can see that now we have those blue features. I used to use a green line to represent as a feature to represent our user. And we use those red columns as a feature to represent item. But now you can see they're all of the same length, which is D, much shorter. Okay. So by this decomposition, we again introduce the embedding into a D-dimensional space. We can sort of go back just to use our content-based approach now, right? Everybody's embedding a D-dimensional space, and preference basically measured by inner product or closeness. And so this is very easy to understand. Now, the ordinary classical SVD algorithm isn't applicable because some of the entries are missing. So this is the objective function we want to minimize. Quadratic loss over non-missing entries. We want to avoid overfitting. We usually add some penalty like L2 penalty over those entries I'm given V. And so it's a nice objective function convex, so we can use gradient descent to solve it. So this is underlying mathematics. And so once we can get this latent factor, then we can, as I mentioned, basically you embed everybody in a d-dimensional space. So we can use, in this case, you use the inner product to represent the preference. So for example, this entry is missing. Well, but just find the corresponding d-dimensional vector of that user and the d-dimensional representation for that item and just do an inner product. And that will be your estimation for that question mark. Okay? And sometimes people move one step ahead and they introduce something called the baseline model to correct the bias. So what is the bias? They look at the matrix R, Rij, and if you've taken 4 to 5 or 4 to 4, well, that's our ANOVA model, right? We do additive ANOVA model. So we estimate our Rij in the following way, and global effect over average plus the user effect for the ith user, and the column effect for the jth column. If it's movie, it will be the jth movie, and then plus the remaining terms, Rij tilde. And then you can do your collaborative filtering or latent model only on the R tilde part. So you remove the user effect and the column effect. And sort of similar idea as what we described before when we do kind of a centered cosine similarity. And it's estimating those items, A, B, and mu is actually very easy. You can just plug into your original L2 loss function. You can add your penalty over A and B and just do your gradient descent. So this can be done pretty easily. Okay. So there isn't actually much to say about the recommender system. Content-based, collaborative filtering, and of course, in practice, there's a lot of tricks you have to utilize for real problems. As I mentioned before, the computation cost is high when you try to find similar items or users. So sometimes you need to pre-cluster them. Meaning I cluster my users, and then when I look for the closest user, I only look for the closest user in that particular cluster. So that will dramatically reduce the computation cost. Another is usually you have to combine multiple recommender system together. And if you go to Amazon, they will say, well, what is the top deal this week? What is the best things in particular division electronics? And what might be something you because you clicked before, now you may continue to be interested in those items. So it's actually a combination of a different recommender systems. Another issue you need to take into consideration nowadays. Nowadays, there is a contextual information, which is a location, time, and a particular device. Are you looking at Amazon on your iPhone or on a computer or on an iPad? And the recommender system should be slightly different. And also the interface. Now, another interesting topic is how to evaluate a recommender system. How would you evaluate a recommender system? So when one of the popular evaluations is based on, view this as a prediction problem or predicting numerical outcome, right? So remember we have this R matrix, some entries are missing. So we can maybe, take some of this out and then give you part of the data and then want you to predict, not the question mark, but predict something you observed. And then predict those scores and look at the, root mean square error, which basically the difference of those what's you taken away from the data and your prediction. Look at the difference square, average, and take square root, right? So that's actually the metric used by Netflix. But there's a drawback for this. Why there's a drawback? If you look at how people are going to use the score you provide or you predict, usually we don't care if you predict something to be 1. We care more about whether this is an entry you predict is going to be 5 or 4, because that means this user is of high interest of this item and we want to recommend, right? So people find out, although the root mean square error, MSE, often used as a metric, but in practice, we are only interested in the accuracy over the cells where the value is actually high, because that's the item they want to recommend. So this is another metric called top K, meaning, you, for example, for a user, you take some of his data out, and then you predict what are the top 5 items he will be interested. And then you compare with, the truth and look at the top K accuracy. And that sometimes is much more, relevant. Another issue is, although we want to predict accurately, but sometimes as the online, as Amazon or other e-commerce website, and they want the prediction to be diverse enough to sort of cover their whole catalog, and instead of just to keep recommending the same thing. And so there's a sort of a balance between the diversity and accuracy. And also another thing is that, serendipity. Is that something, oh, I didn't even know I like this. Thanks for recommending this to me. And that kind of a user experience is also, sometimes you want to have. So that means you may sometimes want to take some risky predictions. Another, in practice, kind of important issue is how to incorporate user feedback. As I mentioned before, sometimes it's hard to know, is this item the user is not interested, or he or she doesn't like the item. And sometimes they will give you some recommendation. They actually monitor whether you click some of those recommendations. Just try to get feedback from the users. And the challenges will be scalability, large data, and data is very sparse, and how to construct that R matrix and code start. How we start recommending a new item just added to the catalog, or a new customer. I don't think there's any sort of a fixed solution for those problems. Just be aware, and those are the challenges. Okay, so let me talk about some of the sort of a new development nowadays for recommender systems. They're all based on deep learning. Now, if you don't know deep learning, you can just think about all the deep so-called neural network, and it's just a black box. You provide data in, you get some prediction out. And those structures, they're going to estimate stuff. Those are the weights over every edges. They basically use a gradient descent. They can estimate it. So just leave it as a black box. So here are the two kind of extension and for recommender system by using neural network. One is to use deep learning to construct latent features for either items or users. I add some link on Piazza so you can look at the original paper. So this is a picture for Spotify. Spotify is the music recommender platform. So what they did is, this is the original audio file. They do some representations. This is the original audio file. And for some of the audios, they have already used that latent factor model and to get a 4D-dimensional feature vectors. Okay, so they go through their collaborative latent factor model, use that R matrix. For some of the videos, some audios, they already get the 4D-dimensional feature vector. Now they wanted to find out whether they can actually directly construct this latent factor only using music itself without user data. So for those data, they have this 4D-dimensional feature. So it's a regression problem. Input is a matrix, output is a vector. You measure by mean square error. So you just throw into your black box, you do your training, and you get this network. Then for any new new sounds, you can put into this filter, you eventually get your 40-dimensional latent vector. So this is how they actually get the embedding for their music. Now, once you know how to create a feature or latent vector for your music, getting the user profile is easy. You can get it something similar in that 40-dimensional space. Another type of idea is just try to get nonlinear embedding and using the so-called autoencoders. So what is the autoencoders? You can imagine you have your item, which could be an image, could be your movie, but described by a lot of features, or an article by those termed TF-IDF feature vectors. So the so-called autoencoders basically is like this. You have your original input, a long vector or a matrix or some audio file. You input into your network, going through a lot of layers. You get a 2-dimensional, and you go through a lot of layers, eventually get to the original dimension as what your input. So you want to reconstruct, okay? And then how you construct the loss function. Once you have the network structure, how you construct the loss function. Input want it to be close to the output, mean square error, that's it, and your gradient descent. Now, once you build up this network, the autoencoder, then you can drop this part. This is your autoencoder. You only need 2-dimensional space to represent your original input. So this is how they so you can imagine by using this network, you can do this music too, right? You can take this music input, go through 2-dimensional, eventually get another matrix. You want them to be close. Now, once you have done this, then you can take this 2-dimensional as your latent vector, 2-dimensional feature for your music. Of course, 2 probably is just, I'm exaggerating. You probably need 40 or even 100. So one type of extension is just to focus on using deep neural network to get a better feature representation of the items, okay? And another type of learning is basically nowadays for a lot of big website, this is actually for YouTube. For YouTube, and I think for Taobao too, they always 2-stage recommender system. So what is 2-stage? They have the first, somebody send a query or, for customers, they're first going to filter out those kind of a huge catalog, zoom into a small choice of items, let's say 50 of them. And so that's the candidate generation's filtering stage. And then they're going to learn a ranking algorithm, which could be a classification algorithm. Just learn, basically they want to learn what is the preference of this user to each of those 50 items. You can get a probability, any numerical number, and then you just rank them. The top 5 get the highest rank, then you're going to recommend to the user. So those are the 2-stage approach. Some of them at the filtering stage, they use probably just simple matching, but only try to train a complicated model at the ranking stage. The ranking stage is nothing different from classification because you previously for this item for this user with that kind of information like his age, a lot of user profile, and whether he will like this particular item. If he liked this item before, then that's 1, otherwise 0. You train a classification model. But of course, you want something more sophisticated than logistic regression. So this is a 2-stage approach. Now let's look at one of these sort of popular sort of model developed by Google for that ranking part called the deep and wide model. So what is a deep and wide model? And the deep neural network, that's a model I never covered in class, which I told you just treat it as a black box. And so the idea of this deep neural network is we can generalize. But for the simple linear regression model, if you do a lot of dummy coding for the categorical variable, you basically remember things, right? So they put them together, and it's called the wide model, which is a sparse, just a simple logistic regression model. To remember, when there's a query for fried chicken, it's very likely it's actually for fried chicken rice. Because sometimes there are some users, like when I order, some of the dishes, I'm very specific. I don't want you to start throwing some random combination to me or generalize. I want this particular, soy latte 2 shots. That's a particular combination. So for that, they want to use a white model to remember this. But still, there's some space for you to generalize. Maybe chicken fried rice could be shrimp fried rice, and and chicken and waffle, and fried chicken actually means this person may like burgers too. So there's some kind of generalization going on, and they put them together. Again, the structure is there, looks very fancy. Underline just gradient descent once you specify the loss function. And I think, yeah, you can actually download their code from Google website. You can train this kind of a deep and wide model. It's not necessarily restricted to recommender system, so you can use it on other classification model too. Okay, so with that said, I think I'm done with recommender system.